For our next question, we want to find the power series representation for this function. So if we have f of x is equal to inverse tangent of x squared. So first we're going to need to find the power series representation for the inverse of tan. And so we know that the derivative of tan x is equal to 1 over 1 plus x squared. So we can just rewrite this as the inverse tan is equal to the integral of 1 over 1 plus x squared. And now we need to remember the cheat sheet, if you'd like to call it that, of 1 over 1 minus x is equal to the power series from n is equal to 0 to infinity of x to the power of n. So in the scenario where we have 1 over 1 plus x squared, let's rewrite it on this side, that is the same thing as 1 minus negative x squared. So let's just put that in. And let's rewrite this in a simpler form. To the power of 2n. So if you want to get the power series representation of the inverse of tan, we'd like to take the integral of what we have just written out because the two are equivalent. So negative 1 to the power of n x to the 2n. Let me just ensure everything is okay. Okay, and so we need to, these don't have any dependence on x, so technically you can pull them out, but it won't have any effect. And so we just need to remember that the integral of x to the a is equal to 1 over a plus 1, x to the a plus 1. So this means that this is going to be equal to the sum from n is equal to 0 to infinity. Negative 1 to the power of n remains unchanged. A is going to be 2n. So a plus 1 is 2n plus 1. So x to the 2n plus 1 over 2n plus 1. So that's going to be the first step. Next, if we want the inverse tan of x squared, we're going to have to replace this x with x squared. So that becomes 4n plus 2. And we know that all of this all holds in the condition that the absolute value of x is less than 1. So let's rewrite that. And finally we get x, we're going to multiply this, so that becomes 4n plus 2 over 2n plus 1. So that's going to be our first answer. So the power series representation is 10 to the negative x squared is equal to the summation from n is equal to 0 to infinity of negative 1 n x to the 4n plus 2 all over 2n plus 1. Next, we will want to find the interval of convergence, and we're going to do this with the ratio test. And you just need to remember that the summation converges as long as L is less than 1. And we need to recall that L is equal to un plus 1 over un if un is this. So L is going to be equal to -1 n plus 1 x to the 4n plus 6 all over 2n plus 2 plus 1 multiplied by, this is going to be the un part, so -1 n x to the 4n plus 2 all over 2n plus 1. And this is going to give us -1. Oh, sorry, it's supposed to be the inverse. To write that, because it's the denominator here. So n plus 1 minus n x to the 4n plus 6 minus 4n minus 2 all multiplied by 2n plus 1 over 2n plus 3. This just becomes -1, and this becomes 6 minus 2, so x to the power of 4, and the magnitude of -x to the power of 4 is just x to the power of 4. So, sorry, magnitude of x to the power of 4. So, sorry, L is equal to the limit as n approaches infinity of this. And so we can just pull out the x to the power of 4, and it just becomes x to the power of 4 times the limit as n approaches infinity of 2n plus 1 over 2n plus 3, which of course cancels to become 1. So this finally means that L is equal to the magnitude of x to the power of 4, and we want this to remain less than 1. And this is the same thing as, remember that x to the power of 4 is equal to x squared by x squared. And then we can make them individual. So it's the same exact thing as x to the power of 4. So this means that the magnitude of x to the power of 4 is less than 1, which means that x, the magnitude of x, must be less than 1. So this simply means that the interval of convergence is going to be when x is between -1 and 1. And that's our final answer.